I see a lot of people are coming on now. For those just joining, what I'm going to ask you to do is I'm going to ask you to mute your microphone so we don't have any background noise. At any time you want, you're free to unmute yourself and ask questions. So I just ask you to keep muted while we're talking, while I'm talking, just so there's not a lot of background noise and people hear better. So I'll start by introducing myself. My name is Greg. I work at the University of Oklahoma in Sims in the School of Meteorology. And I work probably with a lot of your parents, or in a close environment with a lot of your parents or uncles or grandparents or whatever the case may be. And so what I'll start is I'll just start by showing you all the materials that we're going to need today. Okay, so I'm going to flip my machine around here. So maybe your chaperones can help get these if you don't have them already. So we're going to need a pie plate. We're going to need some tongs. We're going to need a clear glass. We're going to need a salt shaker, a can of Sprite. I'd like it to be clear liquid. 7-Up will do, maybe ginger ale. Preferentially not Coke or Dr. Pepper. It'll be a bit harder to see with them. We'll need some flour and a cookie sheet. So what we're going to talk about is, let's see if you can see right here. I've just got a plate here, or a bowl, and you can see inside the bowl, I have some ice, and I also have some water. So my question for you guys is, are these the only two types of water that we can have occurring in the atmosphere, or is there anything else? And you can put any questions you want on chat if you want, or any way you want, okay?
What do you think?
Or you can, I've muted everybody, but if you have a response, feel free to unmute yourself. Is there any other way that we can have water occurring? I'm showing you liquid water and ice. Is there anything else? Okay, I think, Chania, I think somebody's got something in chat. Check for me.
Yes, someone says water vapor.
Water vapor, yes. And what I'm going to show you today, we're going to do a demonstration to show that water vapor actually exists. So first, I'm going to show you a diagram here. I'm going to share my screen here. And I think now, hopefully most of you are seeing my screen. Tanya, are you seeing my screen?
Yes, we are seeing it.
Okay, so let me put it on big screen. So what we're going to do is we're going to talk a little bit about the water cycle. So what we have, and some of you may have studied this in school, we may have some water here, and you've probably learned that you can get steam or water vapor that comes off the ocean, and then somehow magically clouds form. And then you can get rain or snow, and the water flows back into the ocean. But we're going to try and show you that this form of steam or water vapor, which is another form of water, actually exists, okay? So we're going to do that first. So the first thing I'm going to do is I'm going to stop my sharing here. Okay, and what we're going to do, and Ryan, I need you to help me now, okay? This is my son, Ryan. So what we're going to do first is we're just going to open up our can of Sprite, and we're going to pour it into the clear glass. Okay, so let's just do that. And then we're going to put this glass away for later. Okay? Now what I want you to do is you're going to take your pie plate, and you're going to fill it up with about maybe a couple centimeters of water. I want it to be a reasonable amount of water there. And then we're going to put it beside our stove, okay? So this is where I'm going to need the adult chaperone, okay? So here, what I'm going to do is I'm going to take this little tab off the can just to make it a bit easier to do this. Okay, this little thing, I don't know what you call it, but we're going to take it off the can. Just going to put that aside. And what we're going to do is we're going to take our can to the sink, and we're going to put just a small amount of liquid water in there. So very, very small amount. And then what I'm going to do is I'm going to put it on the stove, and I'm going to turn the stove on to high. And we're going to wait and watch until the water in the can starts to boil. So I'll need help from the adult chaperones here, okay? And oh yes, make sure the water in your pie plate is cold water, please. It'll work much better. So while your adult chaperone helps you with the stove, I'm going to share my screen again. And I'm going to show everybody something, okay? So let me go back here. I'm going to share my screen. Okay, and as your can is boiling on the stove, what we have here is we have here this green rectangle represents our can, okay? And what you see on the bottom here, I have drawn some liquid water, okay? Now what happens is in that liquid water, there are a number of forces that hold all those molecules together. There are bonds between the different molecules, and they hold them together so that they stay as liquid. But there will be a few of these molecules that are especially energetic, and they will escape from the liquid water. So think about, for those of you who have a brother or a sister or maybe a friend, imagine that your friend is holding on to you, okay? That is a force that's holding you. Now imagine that if you have a lot of energy and you really start moving around, you're going to be able to break that grip from your brother or sister or friend, okay? And what's happening, as I heat up the water on the stove, it gets a lot hotter, so it has a lot more energy. So therefore, a lot more of those molecules in the liquid water are going to be able to escape from the liquid. So what we're drawing here is we're drawing lots and lots of these liquid molecules that are now vapor, and they're coming out from the can, okay? So I'm going to stop sharing, and we're going to get to some of the more exciting parts here, okay? So hopefully your adult chaperone now has been able to get your can, your soda can, on the stove, and it's slowly starting to boil. And we're going to use our tongs for the next part here. So what we have in this can, we have lots of these water vapor molecules that are boiling, as it starts to boil, it takes a bit of time. They're starting to occupy that space above the water in the can. And at the same time, I also have a lot of air molecules all around me too, in the air around me, such that this can stays in the shape it has, because just like the water vapor molecules in the air inside the can are pressing against the walls of the can inside, there's molecules pressing against the can on the outside, so it maintains this nice shape, okay? So does anybody have any questions so far? Feel free to put them on chat. Your adult can help you, or also feel free to unmute yourself and ask them. Okay, we're going to wait just a while longer. It's not boiling quite yet. And if you touch the can, don't touch it with your hands. We'll touch it with the tongs. While we wait, let's ask a question. Let's say we take 1 inch square on our counter here. So Ryan, let's show about 1 inch here, okay? We have 1 inch here on our counter. How much weight in pounds do you think the air above that inch squared has that is pushing down on the counter? Does anybody have any guesses for me? Feel free to put it in chat or unmute yourself and say it. Do you think it's 1 pound? Do you think it's 1,000 pounds? Do you think it's 3 gazillion pounds? 1,000. We have one guess of 1,000, okay? Well, I'll tell you 1,000 is a bit too high. Does anybody else want to hazard a guess? 1. Well, 1 is actually a bit small. It turns out you have about 15 pounds of air above each inch squared of this counter. So if I take this entire counter here, there's a lot of air molecules above pushing down on that. So maybe all of those air molecules are going to have some impact on our can here. So it's starting to boil. It might be a bit early, but I think it might be ready. So Ryan, let's take a recording of this. I'm going to grab it, and then I'm going to quickly turn it upside down in the water, and let's see what happens. Did everybody see what happened there? The can actually imploded. The pressure of the air surrounding the can made the can crush in. So now, once your cans start to boil, try the same thing with your can of water on the stove. So Ryan, you can get a close-up here of the can. See how it's crushed in. It's no longer a nice, smooth sphere. And if I'd let it boil just a bit longer, sometimes you can have it implode even more. So for example, the one we did on the weekend, if I go through my cycling file here, the one we did on the weekend here, you see, got really crushed in. Okay? So everybody, go ahead and do that. So I'll give you about 3 or 4 minutes while you do that. And again, make sure the water in your can is boiling. And then I'll let people go ahead and do that. And in the meantime, while you're doing that, anybody can unmute themselves and ask any question that they have. And I'm just going to get a ruler and a spray bottle that we'll need for our next demonstration. You can just stay there. Okay. For the next part of our demonstration, we'll also need a spray bottle and a couple rulers. We have one question here. If the water in the can comes out before the can is upside down in the pie tray, will it ruin it? And we also had another question from Sebastian. Why did the can suck up the water as it imploded? Well, sometimes that will happen and sometimes it won't. And the reason why that'll happen is, again, it's just equalizing the force. That's one of the ways. If there gets to be a bit of a vacuum inside the can, because what happens, let's actually look again at our slide here. So I'm going to share my screen again. Okay, so now we're looking at the second part of our demonstration here. What happens when I turn the can upside down and I've removed it from the heat? There is not the same amount of energy anymore. Those air vapor molecules, they're not as energetic anymore. So what happens is a lot of these air vapor molecules are going to condense, or they're going to become liquid water again. So all of a sudden, a lot of these air molecules, you can see there's less of these vapor molecules here than here. A lot of these vapor molecules become liquid. And that means there's fewer air molecules now above the water in the upside down can. So because of that, there's now more pressure on the outside of the can than on the inside of the can. So the can is going to press, the outside pressure from the air is going to press the can inwards. And sometimes water will get sucked up because there's a vacuum here, there's a bit less pressure here. Another way that pressure can be alleviated is if some of the water gets sucked up into the can, okay? So that's what's going on that explains what happens. And this can be really important because I'm going to show you the next slide here. If you look, this is a railway tanker car. So you can see what happened is they decided to clean the inside of this tanker car. And they did it with hot steam. So there was lots of water vapor at very high temperatures inside the tanker car to clean it. Then they sealed it. And then, of course, it cooled down. And as it cooled down, the vapor condensed and became liquid. So there was a lot less pressure inside the tanker car than outside. So the pressure was enough to crush the outside of this railway tanker car. And if you've ever been near a railway tanker car, you know that they are really well built. That's some really thick steel. So that shows how much pressure there is in the atmosphere, and also is a way that I can prove to you that even though you don't see that vapor, it actually exists in the atmosphere. Okay, so hopefully that answers Sebastian's question about why the can sucked up the water as it imploded. So how many did their experiments successfully with the can? Does anybody need more time to do their experiment? Okay, I see a couple hands waving there. I'll give just a couple more minutes, okay? And this is something also you can try again after we finish the demonstration. We can see who comes up with the best can. So this was a can where I got it really, really hot. And here, this one too, I didn't crush it quite as good. Okay, so we'll just keep our eyes on that. Okay, I can see a couple of you still working on the stove. And if anybody successfully imploded their can, why don't you show it up to your camera so we can see? Oh, I can see one there. That's like a Coke can, I think, a nice one that's been crushed in. Anybody else have a can they can show us? Oh, there's another one. Well, that was a really good one from Ryan there. And there's Zeker. Is that Sebastian, I think, has a nice crushed can? Yep. Very good. We got a lot of good crushed cans. Okay. Oh, I saw a high five from Terry there. That must mean they got their can imploded. So if you didn't get your can imploded, you can always try again after we finish. So what we're going to do next is we're going to think, okay, so now we know that we have maybe water and ocean, and we know that we have water vapor. We've shown there's water vapor there. But then the next question is, how do we get clouds? So my question is, and maybe somebody can unmute themselves or type the answer, What are clouds made of? Can anybody tell me what clouds are made of? Water. Okay, that's a good answer. Now, is that liquid water or water vapor?
What do you think?
Liquid.
Liquid. Okay, I heard that answer. That's a good answer. They're basically liquid water. So how do we go from having vapor to liquid? And to illustrate this, we're going to use our can of Sprite here, which we poured into a glass, okay? And you can see here, if Ryan focuses on my Sprite here, that there are a couple of bubbles there. And this is because we have carbon dioxide that is dissolved in the soda. And what happens is a lot of it's not being really liberated because there's nothing there for it to form on. So let's see now what happens. And this, all of our school-age children can do this. The adult chaperone doesn't have to do this. Take your salt shaker or your salt and pour it into your Sprite and see what happens. So here, I'm going to shake my salt into the Sprite, and you can see lots and lots of bubbles forming. Okay, so we've got lots and lots of bubbles forming. So everybody do that, and then we'll try and explain why that happens. Okay. So is everybody able to demonstrate that? Okay. Cool, I see lots going on. So what is happening here is the carbon dioxide exists in the soda, and when I pour the salt in, that allows the carbon dioxide to form these bubbles on the salt. And in the exact same way, what happens in clouds, within the clouds, there's special particles called aerosol particles, and they're like salt. Some of them actually are salt. And what happens is this gives a surface upon which the water vapor can condense on and form liquid. So just like if you had in the pie plate here where we had some liquid water at the bottom, the water vapor molecules in the can formed on the liquid, the water vapor needs a surface on which it can condense. It's just not going to spontaneously turn into liquid. So these aerosol particles act as a surface upon which the vapor condenses and becomes liquid. And that is how we get clouds, okay? And that's what you see, these liquid water clouds. So now you've got your can of Sprite, and if anybody's thirsty, they can take a drink. Ryan, do you want a drink?
Just had a Sprite.
Okay, he just had a Sprite. If anybody's thirsty, you can try drinking it and see what it tastes like. And you're probably not going to enjoy it, but you can try it if you want. Or maybe give it to your adult chaperone. Okay, well then the final thing I want to demonstrate today is after we get all these cloud droplets, what's going to happen? They're very small and they typically don't form out, they don't fall out of the cloud. So how do we actually get rain? Well, how we can get rain is a lot of times what happens is these small cloud droplets collide with each other and they form bigger drops, and eventually they get to be so big they become raindrops and they fall out of the cloud. So what we're going to do is we're going to look and try and see how we might be able to measure the sizes of raindrops. So what we're going to do is we're going to take our flour here, and what we're going to do is we're going to spread some on the cookie sheet. Probably should be about maybe a centimeter deep or so. If there's only one, you probably can do it on half a cookie sheet. If you have a brother or sister with you, you'll probably want to put flour over the whole cookie sheet, and then maybe each of you can use one side. Or if there's 3 of you, probably divide it up into thirds. If there's 4 of you, you probably need 2 cookie sheets. So I'm just sort of distributing it about there. So just spread some of the flour onto the cookie sheet. Now, unfortunately, we have very bad weather today, okay? We go and look outside, there's not a cloud in the sky, it's warm, there's no rain, there's no hail, there's no snow. This is what we call bad weather for a person who studies clouds, okay? So we're not going to be able to measure the actual size of actual raindrops. And instead what we're going to do is we're going to use our spray bottle to make rain, okay? So what you want to do is you want to take your spray bottle now, and you're just going to generate some raindrops and make them fall into the flower, okay? So I'm doing that a bit. You don't want so much that the flower becomes saturated. But what you'll find when you do this, you'll have lots of small little dough balls that get formed when the water hits on the flower. And what we're going to do is we're now going to take our ruler. This works best with a clear ruler, but it'll work if you don't have a clear ruler. And let's measure the size of some of these dough balls. So I'm not sure if my iPhone is good enough resolution here, but Ryan will zoom up on it and we can go and measure the size of that dough ball. So I want everybody to go make their drops in their flour now and go measure the size of your drops.
Greg? It's me.
Yes.
Just show we got this.
Oh, very good.
Okay.
It's leaking on the computer.
That's okay.
Good job. That's a nice crushed can. We're seeing lots of good crushed cans out there. Okay, I see lots of people still measuring their drops. And once everybody's had the chance to measure their drops, I'm going to ask what sort of, or if you've finished measuring your drops, why don't you type in the chat or unmute yourself and tell me some of the size of the drops that you're seeing. Okay, I see still us generating drops. I see people measuring. 1/4 centimeter. I've got 4 millimeters. Any other sizes out there? You can still see some measuring going on. 3 millimeters. 2 millimeters. Another 4 millimeters. Okay, these are all really good sizes. You know, typically raindrops, they range in size maybe from about maybe 1/2 millimeter up to about 5 or 6 millimeters. Sometimes you can get 8 millimeters, 1/2 meter. I think that one's a bit, might be a bit of a typo maybe. That would be a killer raindrop. That would be a good Hollywood movie, actually. So usually they can be about 7 or 8 millimeters, but typically the maximum it'll be is about 7 or 8 millimeters. Because what happens is these raindrops, as they fall, they collide with each other and they start to break up. So let's go and take a look. I'm going to share my screen again. And I'm going to ask, I didn't share it yet. Share screen. Here we go. Share. Make it large. So what I want to ask now is, what shape do you think raindrops have? So we're going to have 2 choices. We can have this choice, which is more like a tear shape, or we can have this shape, which is more like an oblate spheroid. So I'd be curious as to what shape you think raindrops have. So maybe you can put your guesses on the chat again, and people can tell me whether they think the raindrops are more spheroids, oblate spheroids, or teardrops. So put your guess in. Let me open that up so I can see. Option 2. Option 2. Option 2. Okay, good. I like that. And yes, the answer is, if you take a look at actual images, go back to my screen here. If you take a look at actual raindrop images, yes, they are more like oblate spheroids and less like tears, because that's because of the forces of the air molecules acting as the raindrop falls down. Now, what I would like to do for the last few minutes is I'd like to tell you a little bit about how we actually measure cloud particles. And the interesting thing is, some of the very first experiments that were used to make measurements of the sizes of raindrops actually measured them using a technique very similar to what we did today. They used a material very much like flour, was more like a formvar replica, and then the drops fell into the flour, and then the scientists, this was around 1950, used microscopes to make measurements of the size of the droplets. And sometimes those techniques are still used. So I'm going to show you a video here of an experiment that we did about 15 years ago, where we put some of this formvar replica on a film, and we put it in a box, and then we launched it in a balloon through a cloud to show us what the cloud particles look like in ice clouds. So I'm going to stop the sharing of this screen, and I'm going to show a different screen instead. So I'm going to share my screen again. And here I'm going to show a video here. Here we've got a balloon. This is this typical weather balloon that you use. You're going to see there's a train below it, and then there's a box there, which we used, and we're going to go up and measure what's the particles inside these ice clouds look like. So let's play the video. So there you can see it's rising up, going into the clouds. And then we had to retrieve this box with the film and take pictures of what the particles look like. And this is what some of the ice particles in the cloud look like. Because not only can we have liquid in clouds, we also can have ice particles in clouds when they occur at colder temperatures. So we'll show that one more time. So here we have it going up into the cloud, measuring what our ice particles look like. Okay, but now I'm going to show you a different technique that we typically use now to measure what's in clouds. So I'm going to show you another video here. It's going to take me just a second to find it. Hang on. Okay, I've got it now, so I'm just going to have to get it up. Hang on. So I'm going to share my screen again. Why is that not working? Hang on. Let me share that. Okay, let's try it one more time. hope it works this time. For some reason, it's not letting me share that window. Yep, here it's going to work this time. Okay, so I'm going to show you a window here. I think you can see my screen. Can you see my screen, Tanya? In a plane? Let's see, Brian, is that on your phone?
Yeah.
Okay, so this is actually an array used to make measurements of clouds. So here we're flying over the Southeast Atlantic Ocean off the coast of Africa. And you can see, I'm going to show you what it looks like to fly in a research aircraft. It's not like a typical airplane you fly in where there's lots of seats and very insulated walls. Instead, it's extremely noisy. You can see most people are wearing ear protection. And we have the whole cabin of the plane outfitted with different instruments where we might be sucking air into these instruments to measure what the aerosols look like. We also have probes hanging off the wings of the plane to take pictures of the cloud particles, much like the instruments that are in your iPhone. And then we also have radars that you typically see when you look at weather as well, remotely sensing what are on the clouds. So you see all the different scientists sitting here as they're monitoring all of the data that are coming from the probes. So this just shows you what a research aircraft look like. We have maybe about 20 different scientists on board, fewer on some airplanes, depending upon the type of the airplanes that we use. So here, these racks here, they're actually making pictures of the cloud particles. And this is the rack that controls the data system for the entire plane. And then here are people, they're monitoring some of the fuses that used to power the different equipment. And you saw one of them was wearing a life jacket, because on these planes, we'll go as low as about 70 feet over the ocean surface. We're flying over land, we can't go that low, so that we make measurements of the particles that are coming off the ocean. Then we'll make measurements in the clouds and all the way throughout. So a lot of different things that we can measure on these planes to tell us what's going on. So I'm going to show just a couple more slides now, and then I'm going to open it up for questions. And what I want to do here, I'm just going to show a couple more slides. So here, I think some of you probably looked at maps before. This is a map of the world. And just like trees look different depending upon whether you're in Oklahoma or whether you go to California or Hawaii, you'll see a lot of palm trees. You don't see them in Oklahoma. So if you wanted to study a palm tree, you would have to go to Hawaii. You couldn't study it in Oklahoma. Clouds are the same way. If you want to study what a cloud looks like in the Arctic, you have to go to the Arctic. So these boxes show locations where many of us have gone, people just in my research group, have gone to make measurements of clouds. So we go to the Arctic, we go to the tropics, and we make lots of observations in the United States as well. We've been to pretty much every continent to make these type of measurements. And what we do is we use aircraft. So this is an ER-2 aircraft. It's a type of aircraft based off a U-2, which is an aircraft that the Americans used to spy on the Soviet Union and Cuba in the 1960s and 1970s. But now we actually can use it to make observations of what aerosols look like. And because that one flies so high, on that one only one person gets to fly, and he actually has to wear a spacesuit because the pressures there are so low that there's no air that he can breathe, and he even has to be protected because there's just no air around him. So he wears a spacesuit. And here you see here he's getting off the plane. This is in Costa Rica after he's landed, and he's getting off the plane, and they'll take him and do a medical exam after he lands because of the high altitudes he flies at. And then these are some of the different planes that we also use to fly through clouds. I've shown you the videos, and then I wanted just to show you this one last slide. What we do is beneath the wings of the aircraft, we put lots of these different probes so that they can actually measure the pictures of what all the cloud particles look like. So I'm going to stop there, and I'm going to let people ask any questions they might have. So feel free to type it in the box, or if you want, unmute yourself and just ask the question. I'll be happy to answer any questions you might have. And don't be shy. Oh, this is a very good question. Why do you have to put so many equipment? Why were there so many different instruments on the plane? Well, the reason being is cloud particles and particles that we have to worry about in the atmosphere, their sizes can be as small as 1/1000th of a millimeter, okay? And they can be as large as about 10 centimeters. So that means that they cover about what we would call in science 7 orders of magnitude, but it means we have to cover numbers that go all the way from about 1 to 10 million. And if you wanted to count 10 million people, you would do it in a very different way than if you wanted to count 5 people. If I wanted to count people, I can count the number of people on this Zoom meeting. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. That's pretty easy. But if there was 1 million people on this Zoom meeting, I wouldn't be able to go count them all. I would have to use a different instrument. So it's the same way with particles in the atmosphere. They cover very different sizes, so we have to use very different equipment to get these different size particles. And also, the number of them can be very different. In 1 centimeter cube, so that's a volume, or let's say, what's a centimeter cube? It's just like a little very tiny cube. It's smaller than a dice. A dice is more than a centimeter cube. We might have 1,000 aerosol particles in a centimeter cube. But in terms of the big raindrops, we would probably need 1,000 cubic centimeters to have 1 raindrop. So they're very different numbers of particles as well. And then also ice particles have different shapes. Water is easy because they're all spheres or oblate spheroids. But ice can have very different shapes, so we have to have different instruments to measure their shapes. So that's why we have to have so many equipment, because we can measure so many different things. So that was a very good question. Any other questions? Okay, well, I thank you all for spending an hour with me today. So you can demonstrate this to your friends. You can show how you can study clouds in the kitchen. There's a lot of the basic behavior we experience in the atmosphere that you can simulate in the equipment, in the kitchen. So remember, we have water vapor. It's invisible, but we can show it exists because we imploded a can. And then we showed that to go from this water vapor to a cloud, we need a particle on which the water vapor can condense or form upon to become liquid. And then we measured the sizes of raindrops, much like scientists measured the sizes of raindrops 70 years ago. But we've considerably advanced now how we use different techniques to measure all of the different particles in the atmosphere. So thanks for joining us today.